Then let's go for the second and last talk of the session of the morning. So for that, you can see already that Dr. Yamakami.
Okay.
Thank you very much.
Yeah, that's fine.
He's going to take over the second talk, so please go ahead.
Okay, well, thank you very much for the nice introduction. So I'm going to talk about quantum computation and quantum logic. So this is an outline of my talk. I'm going to talk about the relationship between quantum computing and quantum logics. And to do so, then I'm going to introduce a new form of quantum logic, which is called quantum first-order logic, or QFO. Okay. So lastly, then I'm going to present the precise characterization of the resource-bounded quantum computation, particularly the log-time computation and log space computation, in terms of the quantum first-order logic. Okay. So I'm going to explain about the quantum information theory in 4 slides. Okay, very quick. So the physical, well, instead of using some standard classical bits in the quantum computation or information theories, we are going to use the word quantum bits or a qubit over there, right? The qubit is the linear combination of well, we are going to use a very strange notation. This is called the kit notation. The kit 0 and kit 1. So this is a linear combination of 0 and 1. Right? So that's represent the 1 qubit. In the physical sense, maybe you can think about it, the small, tiny particles spinning around. Oops. Okay, so then you can actually think about it in the spin head projecting in which direction, right? The one direction is 1, and another one is 0. Then, but you can think about all possible, positions in between 0 and 1, right? Or you can actually think about it, there is the atom, and the electron is actually orbiting around certain levels around the nucleus, right? The one the orbit is associated with 1, the other one is associated with 0, but then the very funny thing is about quantum physics is that one single electron exists in the many orbits at the same time. So that's why we have the linear combination, or we call it the superposition of the quantum bits. Okay, so another interesting stuff is called the quantum entanglement. This is the phenomena only existing in the quantum states, not the classical situation. For example, this one is a particular the quantum states for the 2 qubits, right? If the first one is 0, the second one is all it turned out to be 0. The first one is 1, then the second one is automatically to be 1, right? But without any interaction between them. So that's kind of a funny thing. But the quantum state is very sensitive to the observation. So if you want to see it, what kind of situation or status of this, the particular quantum state, we have to look at it or observe it or measure it, right? But the measurement collapse make the quantum bit collapse down to either 0 or 1 with some certain probability. So that's the limitation of the getting the information out of the quantum state. Now we are going to use a whole bunch of the notations. The kit notation, the dual notation is called the Brown notation, and so we are going to use the Hilbert space of the dimension k. This is the space spanned by the kit notation here. So this is a vector. And S is the binary string of the length n, right? And H infinity is just the union of all quantum spaces. And the Q string of length n is meant for the unit norm, the vector in this space. Okay? And we use the capital phi sub k to be the set of all Q strings of length k, the k is this form, to the n. And similar to the H infinities, we use phi infinity to be the collection of all the Q strings. Okay, so we associate the Q string with the size or length. The length of the quantum state is the minimum number n that satisfies this form. Right? But the exception is the null vector. The null vector exists in all Hilbert spaces of the different dimensions, but we simply associate the defined the length of the size of 0 vector to be 0, just for the simplicity. Now we move on to the quantum computation part. Okay, early models in quantum computation, the model started in the 1980s. Right, the beginning of the Deutsch, they proposed the quantum version of the Turing machine, classical Turing machine, and the classical Boolean circuits. And more modern things of QTMs are defined in the 90s. Right, the single tape the quantum Turing machine and the multiple tape Turing machines. And the Bernstein's Vazirani's, that's the very nice paper describing the property and the definition of the single tape quantum Turing machine. The multiple tape versions are defined later on, Yamakami and Uzawa and Nishimura. The quantum circuit, the modern days and quantum circuits are defined by Yao, still in the 90s. Okay, so I just briefly to mention the structure of the quantum Turing machine. Quantum Turing machine is just a quantum version of the classical Turing machine. So we have an input tape. Usually, it's an input tape contains the classical information. So just zeros and ones, for example, right? Now we have the work tape and the garbage tape, and we have the finite state control part and the head position and work head position, right? But except input tapes, all the informations are usually quantum. It's a quantum state or quantum situation. So based on that quantum Turing machine model, the standard polynomial time computable definition is using the polynomial time well-formed quantum Turing machines. Or we take the polynomial size quantum circuit. They define the bounded error quantum polynomial time. So this is the extension of the class P, for example. Right? So, but then we are interested in lower complexity class. So we have to attach the index tape. So you're familiar with an index tape right now, right? The index tape gives the address or location of the some portion of the input tape. So we simply write it down the information here, and then we go into the query phase. Then we access this location on the input tape. Okay. Now the log time quantum computability is defined by the log time QTM. So this is this machine consists of the random access input tape, and index tape, and work tapes, and the garbage tapes. The important thing is the runtime of this machine is log n, order of the log n. Right? The BQ log time is the collection of the promise programs solvable by the bounded error the log time QTMs. The promise program means the pair of the two languages or two sets. The one consists of the positive instances. The other one is consisting of the negative instances. So this is the hierarchy part, right? So we expand the BQ log time by appending the alternating quantifiers, starting with an existential quantifier and followed by the universal quantifier and so on. In the end, the machine, the quantum Turing machine, accept with high probability, right? For the positive instances. In negative instances, we do the completely opposite. Oh, sorry, this is 0. Okay. Now, the log space QTM is similar to the log time QTM, but the difference is we do not care about the running time, but the space used for the computation is limited to the order of log n. That's why this is called the log space QTM. The BQL stands for the collection of all promise problems solvable by the bounded area of the log space QTMs. But sometimes it's better to put the restriction on the running time. So if the running time is expected polynomial time, so we write it down to p time BQL. So this is the restriction of the BQL, right? And also we can actually make it a hierarchy. Okay, now we finished all the quantum information and the quantum computation theory, the background of it. Now we move on to the logic part. So I start describing about classical first order logic, FO, the first order logic. Right? F4 stands for the complexity class defined in terms of the classical first order logic. Revich and Lewis in 1984, they explored the close connection between F4 and AC0. AC0 is the complexity class defined by the polynomial size Boolean circuits of the constant depth. But each gate has unbounded fun-ins. So that's an interesting thing. But Immerman used an F4, first order logic, as a basis to describe the P, the polynomial time, and NL, the non-deterministic log space. And the particularly important thing is that the Barrington, the Immerman, and Straubing, they proved that F4 precisely characterized the hierarchy, the log time hierarchy. Right? So now you see that an F4 is equivalent to saying that well, then we can actually do in the hierarchy level in the log time. The Immerman expanded F4 because F4 is a very weak system. So they added the extra operator called the transitive closure operator, TC operator, and proved that an F4 adding this extra operator, the weaker version, the positive TC, is precisely characterizing an NL. But then if you use the full power of the TC to the F4, then that's the log space hierarchy. Okay, so now then we move on to the quantum logic. The Burkhoff and von Neumann, those are famous guys, in 1936, and first discussed the quantum logic. But which is based on the Hilbert's lattice of the closed linear subspaces. It's a very mathematical object, right? And lately, the number of the quantum logics are proposed, a whole bunch of them different kinds of logics. And some of them are actually related to the recent progress of the quantum programming languages. Right? Because now the quantum computers are actually within the reach. Right? So then people are actually talking about the programming languages to operate the quantum computers. Now we have to think about the verification of the programs. Right? Based on the schematic definition of the quantum functions of the Yamakami, and then we propose the new forms of quantum logic, so-called quantum first order logic, QFO. So the quantum version of the FO. So that's the main topic of this talk. Now we are going to explain about quantum first order logic. So I'm going to give the syntax and also giving the meaning of those symbols. So we are going to use the variables, two different kinds, classical variables in lowercase letters, I, J, K, and X, Y, Z. Those are actually referring to the pure state quantum variables. There are two different kinds of quantum states, pure states and mixed states. But we are not going to talk about the mixed state, but the pure state. Okay. So, and the pure state quantum variable has size. Well, the size of the quantum variable is expressed in this, the pair of the vertical lines, right? And the function symbols. So we will use 0, 1, I log n. So this is the plural of the log n, and also n. So those are constant symbols, or the function symbols of arity 0. And the next one is the successor function, and adding 1, right? Qubit. So this is the function symbol of the arity 2. And the qubit I, y mean that the ith qubit of this y. Y is actually the quantum, referring to the quantum state. And x, capital X, so which is called the instance function symbol of arity 1. And this capital X represents a string, the input string, the binary input string of length n. So x of I means the ith bit of this given binary string. So those are the meaning. The predicate symbols, we are going to use classical predicate symbols, standard ones. And also we are going to use quantum predicate symbols, the arity 2. P sub I, P sub rotation theta. So this one is associated with the rotation at the x-axis, and this is the identity. Okay, then we are going to use this notation, S and colon T. So this means that we apply F, either I, identity matrix, or rotation matrix, to quantum state, given as S, and then we obtain T. So this is actually the process of applying some quantum operation. Okay. And we are not going to use them controlled not, because this is definable in our logical system. Right? We will see later on. The quantum predicate symbol functionality 2 with the constant epsilon. Right? So this means that if we observe quantum state S, then we obtain B. B is either 0 or 1, the classical state, right? With some error probability of this observation is at most epsilon. Epsilon is given there. Right? Instead of this formal notation, we abbreviate or simply write this. Okay. So atomic quantum formulas are standard ones, and the quantum logical connectors. Those are the kind of very interesting things. Now we are going to use the quantum and, quantum or, quantum not. The quantum and, so phi and psi mean that in successive computation, first we compute phi, then we compute psi. It's a process of the computation, right? And the quantum order has this form. And assuming that this does not appear in the second argument places of the phi and psi, then this means that this is the one qubit, right? The ith qubit of Z quantum state. If this is 0, then we continue the computation of the phi, and if this is 1, then we continue the computation of the psi. That's the meaning of this guy. Okay. Negation of phi means that the Q is actually the tricky one. It's not the classical negation. It's a quantum negation. So this is the negation. The measurement outcome of phi is negated. Right? That's why this negation does not affect and or. Okay. So this is actually the schematic definition given by Yamakami, and composition, the branching, and the multi-qubit and quantum recursion. So this is actually slicing down one qubit at a time in a polynomial. So those kind of things defined and precisely characterized the polynomial time to quantum computation. But now the third one, the scheme, so the branching scheme. The first qubit is 0, then we apply G, and the first qubit is 1, then we apply H. So this is the basis of the introduction of the quantum OR. Okay. Now syntax and semantics, we just continue here. The quantifiers, we have the quantum classical quantifier of this boundary point, right? And also we are going to use the quantum quantifiers of this point. So this is the for all pure quantum state of the size S, given S. This is 1. The Y false. This is also 1. Sorry. The quantum formulas are defined from the atomic quantum formulas with the quantum logic connectives. We have several, and also quantifiers. Okay, so I'll just give them some examples, right? C0 operation is going like this one. So C0 has two quantum bits. And the first one is 0, then we do not change the second one. If the first one is 1, then we negate the second qubit, right? So this is actually defined in this form using this not operation, right? And also we can actually represent the Walsh-Hadamard transform. And that's the, so this is the transform of the rotating 45 degrees in a plane, okay? And also we can actually express the bitwise XOR in this way, right? And also we can actually define the not equal, Y and Z are not equal is expressed in this way, in a quantum way. So now we have an observation at the end. Okay, all right. So I told you that the P sub I, the P sub rotation, right? We have the first argument place S and the second argument place T. So that separated by colon, right? So this means S is transformed to T by application of some computation, right? So now the first place and the second place are completely different meaning, right? So now we have to introduce the notation, say that the quantum variable y or its component y appeared in the second argument place of the certain quantum predicate symbol. That variable is called the predecessor dependent. Otherwise, it's called the predecessor independent, right? Now the quantifier is called the consequential quantum quantifier if the y appearing here is the predecessor dependent. Otherwise, introductory quantum quantifiers. So for all, is always the introductory quantum universal quantifier. Now we introduce the word introductory quantum quantifier free. So if the phi does not contain any consequential, introductory, no, all quantifiers are consequential, are not consequential, then introductory quantum, then in that case, introductory quantum, if all the quantifier in the phi are only consequential, then the phi itself is called the introductory quantum quantifier free, or IPP free. Now, so we come to the definition of the QFO. The QFO is the collection of the promised problems which are syntactically expressible by quantum sentence of the quantum first order logic. Syntactically expressible means that the promised problem is expressed by the quantum sentence phi in the following way. So we have a constant epsilon, and for any input x, the classical input x, we translate x to be the capital X, and the size of x, right, is evaluated as n. So this is the variable, right, constant, right? So if x belongs to the positive instance, x is the positive instance, the phi is true. And if x is negative instance, then not phi is true. So this is true for all x. fixed constant. So in that case, QFO is defined. The classic QFO is the restriction of the QFO by requiring that an IQQ-free quantum synthesis being used. Now we'll get the result like this one. The classic QFO is simulated by the log time, quantum log time. The QFO is simulated by the BQ log time hierarchy. And also the classical first order logic is simulated by the quantum first order logic. So this shows that the quantum QFO is the extension of the FO. Right? Now, the QFO is a very weak system similar to the classical FO. So we want to add extra operator. So the first one is the quantum version of the transitive closure. Right? And the QTC represents the quantum transitive closure. Right? And this is applied to the phi. The phi is called the quantum Bayer relation. That is the measurement-free, IQQ-free quantum point. Right? And this means that we start with start with I, and then decrementing the counter from I to j by 1 by modifying those x, tuples and x to tuples y's, and we repeatedly recursively repeat this process until the counter goes to j. But then I is bounded by the I log n, the log n. In that case, we just write log QTC instead of QTC. So this is the result we got. The BQ log, the classic QFO plus log QTC. This is in between BQ log time and the BQ log square time. And QFO plus log QFT is in between the log time hierarchy and log square time hierarchy. And this is more interesting things. And classic QFO plus full power of the QTC precisely characterized the polynomial time bounded log space, the quantum log space. And the QFO plus QTC is defining the p-time BQL hierarchy. Okay, so this is the last part. The tabular quantum variables. Instead of using the recursive procedure, we're going to do another variable. That is the tabular quantum variable. This is actually the some of the embodied containing the multiple variable as a single variable, as a sort of function or table, right? If the capital Y is the tabular quantum variable, then we just put I1 up to I sub k. So this is the index of the Y. So we will get the pure state quantum variable. Now the result is like this one. This is the precise characterization of the BQ log time, the BQ log time hierarchy. Okay, so this is the summary of our result. Okay. The last slide here, the challenging open problems. But we still do not know the exact computational power of the QFO or classic QFO, right? We only know the upper bound and lower bound. And also, we do not know the exact computational power of the QFO plus log QTC and the classic QFO plus log QTC. It's nice to have the result, precise characterization. Well, thank you very much. I'm happy to take questions, but probably tonight do not have much time.
Thank you very much. Indeed. We will have time for maybe very short questions, if any, from the audience before we go into the panel. Please, open to discussion.
Maybe very quick, could you please give an intuition about why you call this consequential or introductory
Oh, I see.
The reason
Okay.
for the names. Yes.
Yeah, because there's the first place and the second place. And the second place is the result, somewhat the result of the first place variable, right? It's the computation from the first one to the second one. So, but then if you put the existential qualifier using the same y here, right? That means they exist in the first part. So that comes out of nowhere, right? But if you put the existential qualifier for the second string or second the variable, right? That means that is the result of something else, right? It's you're not taking anything out of blue, right? Because this is completely characterized. That's why we have to separate the two concepts.
One last burning question, if any from the audience.
Maybe it's a bit complicated, but what's the really difference between pure state and mixed state? And how
Oh, I
does
see.
the
Okay.
pure
Well, that's well. In the simple answer is the pure state. You know everything,
Yeah.
right? But the mixed state, you're only knowing some portion of the quantum state. The other parts are actually somewhat hidden.
So that means it's still difficult to apply QFO, your QFO to mixed state.
Yeah, that's more usually if you use a qualifier on the pure state variable or mixed state variable, the power might be different. Yeah, we do not. Well, even in the polynomial time situation, there is some argument.
Well, thank you very much to both the speakers of the session.
Thank you.
Thank you, and of course, you are more welcome to join the celebratory panel.
Hi, good morning. I'm attending an international conference which is called CiE 2024, held in Amsterdam here. So I'm staying in Amsterdam right now. The conference is going on right now, and I gave my talk yesterday morning from 9:30 to 10 o'clock for 30 minutes. Period of time, and I gave a talk about so-called quantum logic. I provided a new framework to describing a new form, new kind of the quantum logic. The connectives and quantifiers used for describing this logic seem to be a little bit different from the existing ones. Okay. Tonight we are going to have the cruise trip and also the banquet, a dinner. But the interesting thing is that dinner will be served on boat, right? So we are sitting on the boat, enjoying the scenery around us. At the same time, so we are enjoying the delicious food, probably the Dutch food or. Yeah, this is the international conference. Probably the food might be international ones, right? From the Western ones and the Eastern one. Well, who knows? Okay, so I'm hoping that the weather during the cruise time, the dinner time, will be fine. Because a few days ago we had heavy rain with thunder. Yeah, so I'm hoping that we are not going to encounter that kind of disastrous weather, I hope. Okay, so I filmed my talk given yesterday morning, and I'm going to upload the video to YouTube and the social media, so you can enjoy it and watching my talk. And hopefully you will get some idea about quantum logic. Okay, thank you for watching. See you later.